Hello, everyone. Thank you for joining us today. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's Hangout on Air. Folks, today we are making a departure from our usual webcast format and broadcasting today's live event via Google+ Hangouts on Air. Today we have Dan Sanderson presenting data modeling for Google App Engine using Python and NDB. Dan is the author of the O'Reilly book, the best-selling O'Reilly book, Programming Google App Engine, and his latest book, Programming Google App Engine 2nd Edition, is available now for early release. We are so happy to have Dan with us today to present this live event for you all. A couple of announcements before I turn the program over to Dan. If you have a question for Dan and what he is talking to you about today, please, folks, there are a couple of ways that you can submit your questions. You can refer to your reminder emails for details there, and you can send an email to webcast@o'reilly.com with your question. You can post it on Twitter using hashtag Google App Engine. As well, we do have a Google moderator page set up, and all of you should have details for that as well. Again, folks, webcast@o'reilly.com. You can send your questions there. Hashtag Google App Engine and the Google moderator page. People always ask, so we'd like you to know that today's Hangout on Air is being recorded, and you will receive access details within 24 hours. And folks, at this time, it is my pleasure to turn the program over to Dan for his presentation. Hello, Dan.
Hi, Yasmina. Thanks so much, everybody. Thanks for being here. This is a presentation about Google App Engine, and we're going to focus specifically on Python today. But some of the concepts here are pretty useful to know about, just about how to organize your code, how to use the App Engine data store. So hopefully it'll be useful to others as well. But we're also going to be talking about NDB, the Python data modeling library, the new one that was just released this year. So it should be a fun hour. Just to introduce myself a little bit, I used to work on the App Engine team. I'm currently employed at Google, and I currently work as a software engineer on Google Developers. That's developers.google.com. You've probably seen it. That's the website that hosts the documentation for App Engine, as well as hundreds of other Google developer products. Google Developers, the website, is actually an App Engine app. We built it on App Engine, and we take advantage of all of its features. So I can talk a little bit about that if you're interested, how Google Developers works, things like that. As Yasmina mentioned, I am the author of the O'Reilly book, Programming Google App Engine. The 2nd edition is coming out this month. The final version is off to the presses, and we should be getting it in a few weeks. You can go to Amazon and pre-order it. You can go to O'Reilly.com and pre-order it. O'Reilly.com, of course, has DRM-free ebook versions for all these books. Should be really awesome stuff. I'm really looking forward to seeing the final version in print. So yeah, this talk is about App Engine. It's about Python. We have a few things to say about each, but the data store concepts do apply generally. We're going to focus specifically on NDB, which is specific to Python 2.7. App Engine supports Python, two flavors of Python. Python 2.5 is what App Engine launched with originally back in 2008. There's a new runtime environment, newer runtime environment for Python 2.7 with a bunch of new features. If you're still using Python 2.5 on App Engine, I highly recommend you try upgrading to Python 2.7. All the latest features are being added to the Python 2.7 runtime environment. The Python 2.5 environment at this point is mostly just sticking around to support people who haven't migrated yet. So definitely take a look at Python 2.7. If you want to use NDB, you have to be on Python 2.7. You've probably seen my previous webcasts, but if you haven't, I am going to start with my usual spiel about Google App Engine, just to explain what it is a little bit. App Engine is a platform for building scalable web applications. Web applications being interactive things that communicate over the web using HTTP, serving websites usually to browsers, that sort of thing. Gmail is a web application. Google Maps is a web application. That sort of thing. It's built on Google infrastructure, so you're actually running in the Google data centers on the same infrastructure that powers those Google products like Google Maps and Gmail. A lot of the same utilities that are used within Google have been made into products and services for App Engine, so you're actually using the same stuff Google uses for its own applications. It's set up in such a way so you only pay for what you use. It's a cloud service, and App Engine will allocate as many resources as you ask for, and only as much as needed. One of the key features of App Engine is you can set a budget for yourself to say, okay, well, I don't want to spend more than this, but App Engine will only use the resources necessary to serve the actual traffic you're getting. So you're only paying for what you're using up to the point of up to your budget. Things that get charged for the number of apps you have, the number of instance hours. An instance is just basically a virtual server running your application, how long each instance is running. App Engine will start new instances as needed as your traffic ramps up. You pay for storage, bandwidth, service calls. These are all very granular, usually down to the gigabyte. And it's free to start. There's a number of resources you can get for free just to start out with, just to play around with App Engine. You can create an app right now without paying anything. You can put stuff in the data store. You can actually serve a little bit of traffic and all that as you're testing. Nothing to pay for up front. I mentioned we launched with Python 2.5 back in 2008. We actually launched with Python 2.5 exclusively. Python was the first language supported by Google App Engine when we launched. And then we added a Java runtime environment, very powerful Java runtime environment. It's a full JVM, so you can actually run other languages besides Java that run on the JVM. There's also a Go runtime environment, the Go programming language, which is very powerful. It actually compiles down to native code, so you get a really fast speed out of the Go runtime environment. And then the Python 2.7 environment with lots of newer features. In some cases, they're using it as an opportunity to rethink some of the things about the original Python environment that was launched in 2008. Of course, we've learned a lot about App Engine since we've launched, and so Python 2.7 is a really awesome reboot in some ways. In many ways, it's backwards compatible, so it's not many changes that are not backwards compatible, but a lot of new ideas and new thought has gone into the Python 2.7 runtime environment. It's meant to be easy to develop. We've got really great tools in the SDK, and it's including a development server that runs on your local computer to actually test out your application without having to upload anything. It just runs locally, simulates all the services and all that. And then there's easy deployment. You can run a command line tool, or usually just click a button and it just uploads your stuff, and then it's running on App Engine. It's really easy. There are no servers to manage. It all happens at a higher abstraction than servers, so you don't have to worry about the operating system or anything like that. App Engine takes care of this for you. It's a really simple model for running these applications at a higher level of abstraction. And this higher level of abstraction is actually quite familiar because it's based on standard technologies. In the Python world, the Python runtime environment, you're using WSGI, so you can use any of your favorite web application frameworks and all that. The Java I mentioned is the JVM and servlet-based, all very familiar. And still, it's a high enough level of abstraction that you're worrying less about how to keep servers running and all that, and you're just coding your application and you just focus on the behavior of your app. So today we're going to talk specifically about the App Engine data store. We're going to cover some basics of the App Engine data store and how it works and how those concepts translate to the NDB Python library. We're going to talk about data modeling, some of the data modeling features of NDB, how queries work, how transactions work a little bit, and some really cool features that are specific to NDB. If you've already played with Python on App Engine, you've probably seen the ext.db library, the original DB library that launched in 2008. NDB is sort of I used the word reboot already. It's NDB is kind of a reboot of DB to sort of rethink some of the API concepts, clean up the API, clean up the implementation, and add some really cool new features that we've learned are extremely important to App Engine applications. Things that you would be building manually are now part of the NDB framework, basically. One of these features is automatic caching. If you've listened to some of my previous talks or even read my book, the book certainly talks about a very common design pattern where you're storing something in the data store, but then also storing a copy of it in memcache. Memcache is this distributed cache, global cache that lets you just retrieve things quickly. It's not durable like the data store. So data store is permanent and durable, memcache is less durable but much faster. So if you've got objects that are being read really frequently, you can check to see if it's in the memcache, and if it's fallen out of the memcache for some reason, you can go back to the data store and then put it back in the memcache, that sort of thing. Normally you would set this up manually, and it's so common that almost everybody does it for a lot of things. NDB now has this as an automatic feature, and we'll take a look at that. There's another kind of caching that we'll talk about as well called in-context caching. I'll talk about it when we get to it. As usual, for my webcasts, I've prepared more material than I have time for, so the next few items we're probably going to get glossed over. NDB has several other really awesome features. The batching API, again, if you're used to the old database data store interface, you're probably familiar with batch calls, the ability to call a single data store operation to perform multiple things at one time. Batching is still a feature of NDB, but there's also an automatic batching feature that's really compelling and makes NDB really powerful. Same with asynchronous calling. If you've seen calling services asynchronously, where you can make a call and then go do other stuff while the call is in progress on the service side, that's also a feature of NDB, and also something that NDB can manage automatically. A really compelling extension of this is something called tasklets. Hopefully I'll have a little bit of time to talk about what this is, but I'm going to defer you to the official documentation on tasklets when we get to it. But lots of really great stuff. Hopefully we'll have time to get through at least some of it. I want to leave some time for your questions at the end, so please use the Google moderator or any of the other things that Yasmina mentioned to send in questions. I'll probably just stop talking at 10:50, 10 minutes to 11, to start answering questions, so I'll just sort of cut myself off when we get there. Let's see how far we get. So, the App Engine data store. Let's just start from the basics here. The data store is meant to be a global service for storing data. It's scalable in the sense that you can keep putting things into it, and it doesn't slow anything down. You can put an arbitrary amount of data into it. It's queryable, so the things you put in get indexed, and you can ask questions about the data like you would a traditional database. This data is spread all over the place, but then when you create it and update it, it's updating indexes so that you can actually ask questions about the data, just as you would expect, like how many people live in San Francisco, if you've got a bunch of people records, that sort of thing. It's also transactional in a really important way. We're actually not going to talk too much about the transactional features of the data store today, just because the API is straightforward and similar to the original DB library. But we'll get to it a little bit, but we're not going to cover it in too much detail. But it's good to know that the data store is a transactional data store. You can actually operate on multiple pieces of data in a single transaction, a full commit or a full rollback, all that other good stuff. So the data store stores these records, which the data store calls entities. It's not quite like a relational database. It's not storing it in a table. It's probably best not to imagine it as in a table, but entities are more like objects. These objects have keys, so you can fetch them easily by key if you know the key. The key has a couple of parts. Every entity has a kind. So I mentioned, people. If I was storing people in the database, I might have a person kind, and that would have some aspects to it. So I can ask the data store about person entities. Then, of course, every entity has an ID associated with that, and IDs are unique to the kind. So I could have person number 1, person number 2. I can also, instead of using numeric IDs, I can use string IDs assigned by my application. There's more to keys than that. We'll talk about it a little bit when we get to transactions, but that's the basic idea. The actual data of an entity is stored in properties. These are name-value pairs. Values are typed, so there are multiple value types you can support, including strings, integers, that sort of thing. We'll talk about that. So you can access these properties by name, and also in queries you can refer to these properties by name. So if you imagine what a Python interface might look like for something like this, certainly what we would want is for entities, which are these objects with properties, to be somehow represented in the interface as Python objects with attributes. So this is what we would hope to see. There would be some way of creating a player in a game, right? So imagine we're setting up a game. We've got some way of creating a player entity, which in Python would be a player object. And then the player's name would be the name attribute. The level of the player would be a level attribute. You can assign to the attribute. So here I'm assigning a string to name and a number, an integer to level. I'm also assigning a date time to an attribute called createDate. And then when I'm ready to store this in the database, I just invoke a method on the object and just say, please put this in the data store. That's what we'd like to see. And thankfully, this is exactly how it's set up. But the analogy with Python, the Python objects, is pretty direct. And we'll see more about that. In fact, an important aspect of the data store is that it is schemaless. It does not keep track of the types of the values in the property. Well, it keeps track of the things that are actually assigned, but it's not going to prevent you from using a different type for the same property in a different object. It's just like Python raw objects. It's just going to let you store whatever on these properties. So here I've assigned a level of an integer 7, but then somewhere maybe I've made a mistake and I've created another player with a level of warrior, a string called warrior. And of course, at some point I'm going to maybe invoke some kind of operation on the level property, and it's going to choke on the string because it's not an integer or something like that. You'll notice here also that I can create a player without a level property, which may or may not be a problem. I say may or may not because you might actually be taking advantage of the schemaless aspect of the data store for some things. So that's actually really useful in some cases. But in general, you kind of want some predictability when it comes to the data. So you need a way to structure this and make sure that every player has a level and every level is an integer, that sort of thing. So that's where a library like NDB comes in. NDB is a data modeling library. It runs entirely in your application code, and I want to emphasize that especially. It's not something that adds features to the data store itself. The data store is still schemaless. You can kind of see why the data store has to be schemaless, right? Because it's scalable. You can have millions, even billions of these records, and if you want to change the structure of your data, with a relational database, you can go in and modify the schema of a table, but of course that can be a very lengthy operation. And so the data store representation of that is just to be upfront and honest about that, to say, look, if you've got billions of records and you want to change them all, you're going to have to change billions of records. There's really no getting around that. And so the data store does not bother enforcing that itself because it has to manage billions of records at a time. So if you have code running in your application that can manage this, you can pretty much be assured that as your application is creating entities, it's going to conform to a structure that the application is expecting, and as it's getting entities back out, it can update those entities to conform to that schema, that sort of thing. But the NDB is a library that runs entirely in your application code to manage that. It's very similar to XDB, which launched with App Engine in 2008. NDB was started by Guido van Rossum, whom you may know as the creator of Python. He's also a developer on App Engine. As he started as sort of a side project, as an open source project, and it was just added to the general available SDK in App Engine version 1.6.4, which was back in March of this year. So it's actually pretty recent, but it's been in development for a while. A lot of people have been playing with it while it was in its open source form. And now it's generally available for everybody. Unfortunately, March 2012 is a little bit too new to have made it into the second edition of my book, which is kind of why we're doing this webcast. It's sort of a little bit of an addendum for the book. We'll try to get it into the next edition, but the book right now mostly covers ext.db just because NDB is just new. But it's stable, and it is part of the SDK, and I highly encourage you to start using it if you can. I mentioned it does require Python 2.7, so if you're not on 2.7, you need to upgrade to use it. So here's an example. Again, if you're used to ext.db, the old one, this is going to look very similar. The library name is now NDB instead of DB. The way you manage entities is you create a class that's going to represent objects that correspond to these entities. The name of the class is the kind of the entity. So here I'm creating a class named player, which I'm going to use to create entities whose kind is player, and that name is going to be important as it shows up in the data store. The player class is a subclass of ndb.model, and it has several class attributes that I've defined here that declare the structure of a player entity. So the class attribute name is this special kind of object called a string property, which is more of the model for the property. You can think of it as a container or something like that. Level, we've got an integer property to make sure that that's an integer. Create date, there's a date time property. And here is a simple example. This is exactly what we were hoping for. P1 is just I instantiate the player class, and sure enough, I've got a player object now. I can assign a level of 7, and I can store it into the data store with the put operation. Nothing actually accesses the data store until the put operation here. There's no remote procedure call from your app to the data store until you actually try to store things or get things. So actually instantiating the object all happens locally. And you'll notice here in the second example, I can no longer assign a string accidentally to the level property because the level is modeled as an integer property. So that's actually going to raise an exception. Yeah, so you can see how this works. If you're kind of new to Python and you're just learning about Python classes and objects, this might look really weird, that this class attribute can provide some kind of structure for your data attributes. This is actually managed through some mechanisms within Python called meta classes and overriding the ability to set attributes. So there's some clever stuff going on that's a little bit not quite traditional for class attributes. But as you can see, it's really, really powerful. It allows you to create these APIs where you can define structures for objects. If you're familiar with Django, for instance, the Django web application library, you may have already seen this before, and it's doing the same thing. So that, I can also create a player object with passing the values for the properties directly into the player constructor as just keyword arguments. You can see here it's creating an object here. It's representing a data store entity. It's got a key. Its kind is player. It's got name, level, and create date attributes. It doesn't have an ID yet because in this case I've written it so that the system is actually going to assign a numeric ID. It's going to be guaranteed to be unique and all that. But it only does that when I actually create the object in the data store. So once I actually call the put operation, it goes to the data store, it fills in the ID with a unique number, and there it is in the key. It becomes part of the key from that point forward. The put operation actually does return the key as a key object, so you can manipulate it further if you want, or you can just ignore it. Now, of course, once this is in the data store, I can go and create a key object. This is one way to create a key object in NDB. You call the key constructor. You give it the kind. And in fact, I believe you can actually give it the class object itself without the quotes. So right now in this slide, I'm using the string player, but I can actually just say player, which is a reference directly to the class. That's really useful, and that's a theme that shows up throughout NDB. It gives you a little bit more safety from accidentally typing incorrect strings or mismanaging strings that represent names by allowing you to refer directly to the class that you just created, including the class attributes. Gives you a little bit of extra safety there at runtime for Python. But here it's creating a key that matches the key of this entity. And when I call the get method of the key, that actually goes to the data store and gets the entity and pulls it back into the player variable. And then I can just refer to its attributes as before. Its properties are attributes of that object. So I can just access them as I would expect to from an object. So NDB is doing something really powerful for us here. It's helping us model our data. And you can see why that's necessary. The data modeling allows you to declare the entity structure, the attributes or the properties that are in it, and what types they are. It allows you to validate those property values, and we'll see there's some really powerful features here for data modeling, where not only the type can be validated, but also ranges of values and other things you might want to check to sort of further limit what's allowed to be stored in these things and get better safety within your application as you're creating entity data. And it also provides this Python-like class object interface that's really easy to use within Python. So as we've seen, to create entities in the data store, to set up a data model, you subclass the ndb.model class. The name of the subclass is the entity kind, in this case, player. You use class attributes to declare property names, types, and parameters for those types. And so, we've seen name is a string property. Here's another version of the create datetime property using the datetime property class. I've actually passed a parameter to this one, auto now add equals true. This is really useful for datetime properties. I do this all the time where the property class itself, as one of its automatic features, is if you don't set a value for it when you're creating a new entity, it's just going to use the current system date and time on the application server and just fill it in for you. So it's a really easy way to automatically populate these things. But again, this is all managed within your application code by NDB. It's not the data store doing this for you, it's your application code. In general, NDB provides lots of convenient ways for organizing your code, and this is just one of them. It allows properties to have these automatic behaviors. Here's a list of the supported data types in the data store and their corresponding property classes. We've got integers, floating points, Boolean values, strings, dates. There's also a geographical point, which is a latitude and longitude in a single object. That can be really useful. The user object that comes out of the user service when you're interacting with Google accounts is also its own data type within the data store. So you can actually just say, whoever signed in, I'm going to associate you with this object. And there's some special stuff going on there to make sure that that's consistently referring to the same user. You can also store keys as values. This is a really important way to model relationships between entities. If one entity wants to refer to another one, it can just store the other's key as one of its property values, and you get this sort of soft link between the two objects. None is also a value type for the data store. A property value can be none. There's no way to model this. Pretty much any property can be none unless the property class forbids it, which is another thing that the property class can be doing. There's an important difference between a property whose value is none and an unset property, a property that hasn't been set on an entity. That's really important when we get to queries later on. We're going to talk about how properties are indexed. They show up in these indexes. If an entity does not have a property with a given name, then it will not appear in indexes for that name, for that property name, because it doesn't have it. But if it does have that property and it's set to none, then it will show up in those indexes with a value of none. So that's an important distinction to keep in mind. So the declaration can specify parameters. One such parameter that any property class can take is required. If you say required equals true, then the value cannot be none. It must be a string of some kind, if you're using a string property, obviously. Another one is the default property. A property can have a default value, so if it's not set when it is the entity is created, that value will be filled in by default. So, and everybody starts at level 1 in this case, so I don't have to bother setting it every time. You can also do things like choices. So if I set up a property and I only want, it can be a string, but it has to be one of several strings, I can use choices and say to the property class, please don't let me set a value other than one of these to this. So I've got a character class property. A few others that are kind of interesting. Indexed, all properties, well, most properties of certain types are indexed by default. That means they show up in indexes. We can talk about that later. To save space, you actually are filling up space with those indexes, and it also takes time to save properties to these indexes. If you don't need them to be mentioned in queries, you can actually say, please don't index this property. I just want to store it with the entity. I just want it to show up when I get the entity. So you can turn off whether it's indexed or not. Repeated, if you're already familiar with the data store, and in the book I call them multi-valued properties. It's the ability to add more than one property of the same name to a single entity. So it's the ability to repeat the property. You can have more than one character class or something like that. Very powerful feature. In the past, we've sort of treated this as like, oh, it's like a value that's a list, but it really isn't. And NDB does a better job, I think, of representing the real story here, where what's actually happening is it's more like more than one property with the same name, as opposed to one property that has a list of values. But in the Python interface, it really is useful to treat it as a list, and so it does show up as a list in the Python interface. But this is really what it is. In NDB, you actually have to declare your properties as repeatable in order to be able to store a list value on it. But any type can be repeated. In ext.db, you actually needed to have a list property, which was a little bit harder to manage. And you can also specify a custom validator. You can imagine that each of these property classes is doing its own validation. Oh, this value must be a string. This value must be an integer. This value must be not none, or one of these choices. You can actually specify your own custom validator function. There's some really cool new property classes with NDB that weren't present in the old one. I really like these because they capture some common patterns that just people have been building these themselves over the last 4 years. I know with the developers.google.com, I personally implemented a JSON property class because we were storing JSON message objects values in the data store as properties. And sure enough, they added that to NDB. So there is now a JSON property. Basically, all it's doing is it takes a Python object, dictionaries or lists of dictionaries or anything that can be represented as a JSON property, and just ensures that it is a value that could be serialized as JSON. It's something that you could dump into the simple JSON library and get something else out. It'll automatically compress these values for you. That saves some data space on the thing. Of course, compression takes time, CPU time, once it's actually in your application, so you may not want to set this to true, but it is a feature of that. Same thing with pickling. Pickle is another way of serializing data in Python, and you can do the same thing here to store a pickleable value, and you can also compress it if necessary. So they're very similar in purpose there. There's now a generic property class. All of those data types on that table back there on the left-hand column, the raw data types, those are the data types that the data store knows natively. The data store itself, does not know much more about how to validate any of these things. It just has a set of raw value types that it supports. The generic property allows you to have a property that can take any of those value types. So there's no validation going on. It just says this is a generic property. You may not necessarily use this in modeling, or you may, I'm not sure. You may want to have a generic property that can be of multiple types, but then have some of these other attributes. Generic property shows up in other cases as you're playing with the API. There's this really cool one called a computed property. Oftentimes, you want some kind of automatic behavior to store additional data on your entity based on other properties in the entity. This allows a single property. When you save the property, it'll actually compute the values for these computed properties automatically. So from the application's perspective, it's a read-only thing. You're setting up a read-only property whose value is some other data that's being pushed through some function. This can be really useful in a case like this if you want to do case-insensitive string matching, for instance. I'm storing a last name as a string property. I don't want to think about having to also go back and store a lowercase version of the name. I don't want to, it could be error prone if I have to do that manually. So I just tell NDB to do it for me. I set up another property called last name LC, and I say the computed property is a function that takes the last name of the entity, that last name attribute of the object, and calls the lowercase function on it, and that's what actually gets stored in the last name LC property on the data store. Now it is actually stored. It's computing these values and storing them in the data store, so then I can go back and perform some kind of query on last name LC and ensure that all these values are lowercase. So sort orders are going to be based on the lowercase version of the last name, and I can do direct queries and even some range queries based on the lowercase values. So that's a very simple example of how computed property is useful. This is a really interesting one. If you've got structured data, and you usually do, I often end up storing these sort of hierarchies of information inside an object, and I want to store this hierarchy, represent this hierarchy somehow in my data model. In the past, I've sort of not bothered with trying to have queryable stuff. Like if I want to store like a hierarchical structure in something, I just sort of push it into a JSON structure and then store the JSON data. And it's okay. Well, there's no way in the world I can query off of that property because it's just a bunch of JSON data. How am I possibly going to query off of it? Structured property allows you to maintain some kind of structure within, like a hierarchical structure, within a model, but still be able to access those properties as queryable things. So if I've got a structured property, I can actually use another model class. I'm just sort of reusing this model idea to create basically classes for these substructures that are being stored on properties. I create a model subclass to model the property value, and then I say structured property, this is what it is. The fields of those inner models become properties of the original entity. So in the code, the value is an instance of the model class, and it's like I'm storing an object as the property value, an arbitrary object as a property value. In the data store, the fields of the inner model become properties of the main entity. It's not creating new entities and setting up references or anything like that. These are actually properties of the main entity. So you can query these properties using the query interface offered by NDB. So a really powerful idea, and really not that complicated once you think about it. So kind of an arbitrary example, I've got a separate model for representing where a player lives in my game world. They've got a sector, a house number, roof color, or whatever. And then the player itself has a home property that's actually a structured property based on this player home model. Now, I may not actually ever instantiate player home and store it as a separate entity. I may or may not need to do that. I'm just using the model facility to represent that structure. So now I can create a player, but I can also set its sector. I do believe I've left out a line here. I do have to create a new player home object instance here to assign it to home. But then after I've done so, I can refer to the sector and house number as sub-attributes like that. So I do need to fix this slide. I have to instantiate player home. But I'll go back here just to send that point home, though, that once it comes to queries, the property of the sector, if I wanted to query by sector or something like that, the property name is home.sector. That's actually the name of the property on the player object. It is not a separate entity that I'm referring to when it comes to the query. Yeah, we can look at that in a moment. So queries. Data store is queryable. These property values can be hunted down, and you can ask for a bunch of entities that are results based on comparison operators, things like that. Queries operate on all entities of a particular kind. There are some limited sets of queries you can perform on entities of all kinds, but for the most part, these indexes that I'm referring to are organized by kind and based on property values. So I can have queries with filters. I can say, give me all players whose level is greater than 5. I can sort the order of the results. So I can say, give me the players in order of score descending. So give me the higher score players first and on down. It can return full entities. That's usually what you want. You can also return partial entities. These are called projection queries, a little bit of an advanced subject, which I'll mention in a bit. Or you could just get the keys for these things. That's often a really important performance concern, or a way to sort of minimize the amount of data coming back. If you've got a situation where I just want the keys, I'm going to do something with this data later, maybe I'm going to store these results, these keys later, to be processed by a batch job later or something like that. It's really useful to just get the keys back and worry about fetching the entities later. Queries are scalable. The scalable feature of queries, this still kind of fascinates me. The speed of the query is not affected by the number of records in the data store. It is only affected by the number of results. It's not really an intuitive idea, but in order to get this magical scalable effect, all queries are pre-indexed. So at no point is it actually going through every single entity in the data store and checking to see if it matches this criteria. It is creating lots and lots of tables behind the scenes to make it really easy to answer the questions that you're going to ask. App Engine maintains a set of built-in indexes based on the properties that you have. So straight tables that sort of line up keys and property values based on a per property basis. These are often what you'll use to perform simple queries. If you say, well, if I just do the simple query of give me all players whose level is greater than 5, it's going to go to the built-in index for level, player level, and say, okay, scan, scan, scan. It'll do a really fast scan on its scalable infrastructure to get to the first record whose level is greater than 5, and then it'll give me all the others below that. So these indexes are sorted, and they're all set up to answer these questions in a really fast way. Some questions cannot be answered with built-in indexes, and so for these you have custom indexes. Indexes cost storage space, and they also cost time when you are storing or updating an entity. So the built-in indexes are fine. They come for free. They're free. They're storage space and time, but you get them, and there's no need to worry about those. Custom indexes for fancier queries, you actually have to specify in advance which indexes you need for your queries. So these custom indexes, you do have to configure yourself to say, yes, please spend the time and the space so I can answer these queries for me. Thankfully, the development server actually helps generate the index configuration for you. So you don't have to put too much thought into this, but it is something you need to be mindful of as you're testing in your development server and it's creating this index configuration file for you. Later on, you may need to go back and prune some indexes and get rid of them so that you don't have extraneous indexes sitting out there and spending more time and space on queries that questions you're no longer asking. In NDB, you get a query object by calling the query method of the class of the kind that you want to query. It's kind of a mouthful, but I hope that makes sense. Just look at the first line. I want to ask a question about player objects, and so I'm going to get a query off of the player class that I just created. If I say nothing else, just the query object I get back says, well, give me all player objects. It's not actually executing this query yet. It's just setting it up. So right now I've created a query object that represents the query, give me all player objects. I can also set an order, a sort order for the results that I want, and you can sort by multiple things in the order that they're specified. So in this example, I'm sorting by level first in ascending order, and then if there are any ties, or if there are multiple players with the same level, within those I'm going to sort those by score descending. This is the syntax for NDB. It's actually using the reference to the class attribute that we set up in our data model to refer to these properties, these property names. So again, you get a little bit of type safety here when if you've made a typo in your code or something, it'll actually error if you say, well, wait, there's no actual class attribute in your model named level or whatever. This helps you out. This is, I think, really clever, this use of the negation operator on the class attribute to indicate, yes, this is actually a descending sort order. So you're actually got a positive and negative values of these class attributes representing ascending and descending sort orders. So really straightforward and hopefully intuitive. You can also apply filters, and here filters are actually using the actual comparison operators in Python as you would expect. So I can say player level, I'm referring to the class attribute, greater than or equal to 5. This makes sense to NDB. It knows exactly what you mean. You're creating a filter where I only want entities that match that. And same with character class, I can do a comparison with a string. There are other ways. Throughout NDB, there are some really intuitive ways of passing these arguments around. So as a shorthand, you can actually just say pass these filters to the query constructor itself. You can look in the documentation for all the possibilities there. But usually, if you think it might work, if it makes sense that it would work, it does. So not every syntax is going to be represented on these slides. Once you actually have a query object, you can just fetch some of the results, and fetch does take a number of results to fetch, so it's going to go out and get exactly that number and send them back to you. And it'll give it to you in a list, so you can just iterate over them and access each of those like the original objects. It's just creating those objects in your Python runtime environment. You can also specify other parameters, so if you want to just get the keys and not the full entities, you tell that to fetch. Say, well, just give me the keys, please, and don't fetch the full entities. That's faster. Just like as in the previous database, the DB library, you can actually use the query as an iterable. So this is a very common pattern. I just say, well, okay, I've got this query, and I'm just going to iterate over it. There's no stopping point here. You're going to have to stop the loop yourself, because what it's actually going to do is fetch these results in batches, and it's just going to keep doing them until it either runs out of results or until your request handler runs out of time and can't execute any further. But that's a really simple way of just iterating over the query results. Just take the query object and iterate on it. In many cases, though, you're actually going to want to pass some parameters to this iterator to sort of modify some things. So here's an example of doing that using the iterator interface, but passing in some parameters. So if I just want the keys, I call the iter method of the query object, and I get back an iterator that I can use in the syntax, but it's got these parameters to it. If you've used the data store before and even the previous stuff, you might have used the data store administrative interface that lets you perform queries in this sort of limited syntax called GQL. It's meant to be sort of SQL-like and easy to use and pretty familiar, and as you can see, it is. GQL is still supported in NDB. It's got its own way of doing that, so I can perform GQL queries like this. I won't go into any more detail, but it is supported. There are operators. There's a not equal operator, which does exactly what you think it does. There's also an in operator that says, well, it does this value match any of these? These are special. They are supported, but they are implemented in a special way. They're implemented as multiple queries. So these are not native operators to the data store like less than or equals or less than or equals or greater than equals are. So you can imagine that not equals is basically two queries. Are there any results less than warrior in the sort order? Are there any results more than warrior in the sort order? And that's what it's going to return. If there are any that are exactly warrior, those won't return there. So that's two queries using less than and greater than. In, of course, you can imagine it's a separate query for each of those things. Well, are there any that match thief? Are there any that match mage? So that's what's actually going on. So that even though this is a convenient syntax for doing these things, beware of certain limitations of doing it this way. It gets a little bit complicated, and I don't have time to get into it much further. NDB actually has a way of specifying sort of arbitrarily complex logical expressions using and or. Here, these are really simple versions of and and or, where I've got two filters and an and. The and is what you think it would be. So before, if you were applying multiple filters to a query, that's just an and. So there's really nothing special going on there, but there's a special syntax for supporting and. Or, just like not equal and in, actually has to be implemented in multiple queries. But it does. It has this convenient syntax that's kind of intuitive. And in fact, these clauses within the and and the or can also be more ands and ors. So you can actually have this structured query that's sort of set up as a bunch of ands and ors. The query gets normalized into what's called disjunctive normal form before being executed. And so there are some concerns about that. Again, look at the documentation. You don't want a really complex query turning into this massive thing that takes a really long time to execute. It becomes a bunch of different or clauses and a separate query for each one. But it is a convenient way to structure these queries. I mentioned that you can get just certain properties out of these entities. Now, it's still important to think about entities as objects as opposed to rows in a table. So you might be used to, in SQL, in a relational database, to be able to say, well, instead of select star, just select certain fields, and then you can reduce the amount of data coming back and that sort of thing. App Engine handles this with something called projection queries, which basically is kind of what I just said. So it's not that complicated. You can just say, well, just give me these fields. The clever bit is that it's saving time by not going to the entities themselves in the data store. It's actually taking the index table that it's using to answer the question and getting the values directly out of the index table and passing them back to you. So that's the sense in which this is a special kind of query. That does mean that any query that is going to be, any property that's going to be part of a projection has to be able to appear in an index. And so I mentioned that some properties may not be indexed if you disable indexing or if you use particular value types that aren't indexed. They cannot be used in projection queries. This is the NDB syntax for that. It's just a parameter to the fetch. As before, I mentioned that some of these parameters can be placed in other places. This can also be a configuration for the query, options to the query itself, as opposed to the fetch. Look at the documentation. It's pretty intuitive, and you can put it in different places. But as you can see, it's just a list of references to these attributes of your class. So what's coming back from this example query is the player name comes back, but the player score is not. So the score attribute of the object is not set. Cursors are a really powerful idea. When you perform a query normally, you're just getting the first result that it finds that matches the filter, and then it gets as many as you ask for after that, whether it's all of them or some of them. But there are many cases where you've got like a very large result set, and you want to sort of handle them in batches. So maybe you're showing somebody their email. They have thousands of messages in their email inbox, and you only want to show them 20 at a time because it would just take too long to get all thousands of them and put them up on the screen. So you need a way to say, okay, well, get me the next 20 after this. So if you actually seek by count, I mean, if you show the first 20 rows and then want to show the next 20 rows, one not very good way to do it is to ask for 40 and then just show the last 20 at the end. That's really slow. There is a way to perform an offset to say, okay, well, start at the 20th and give me the rest, but that's still going to be slow. The data store still has to perform the entire query and then count down to the 20 if you give it the number 20 before it can give you the others. So a better way to do that is if you've already performed the query can generate a cursor, which is just like a little bookmark in the results, so that the next time you perform it and with the cursor value, it doesn't have to do any further scanning. It's remembered where it left off, and it can jump to that just as quickly as it could jump to the first result. So it's jumping to the cursor and then continuing down. This is a really important technique for a bunch of things. And it's important because these cursors can be used in later requests. So I mentioned, you're displaying a page of results. Somebody clicks next, on your user interface. They're actually performing another request that can say, okay, I want to start here this time, and it can keep going. These cursor values can be passed around as data and reused later. So it's great for paginated displays. It's also great for batch jobs, a really important technique for using the task queue to execute these batch jobs. I'm going to speed up here because I'm actually already at time and I want to get to your question. So here's a simple example of using cursors. You tell the iterator, the query iterator, please, as an option, please produce cursors. And then when you're done, you can actually test whether there are more results. There's has next, which is a little bit slower but more deterministic about, okay, I can definitely see the next result that involves a data store call. There's also a probably has next, which is usually good enough for something like a paginated display or a batch job. You can say, well, it's sort of a fast check. It's okay, I think there probably might be more results later, and then you can adjust your behavior afterwards. You get a cursor value. There's a way of getting a sort of opaque string that can be safe to pass to a hidden value in a form or something like that that the user can use. You can pass that value around. And then in the next request, you construct the cursor from that string and just pass that as a parameter to the query and just keep going. The query does have to match what started the cursor, so the same kind, the same filters and sort orders has to match so in order to find the cursor in the storage. Pagination is so useful and so common that they've actually built a convenience function directly into NDB for this. It makes it really easy to just get pages at a time. This is what it looks like. Go check it out. It's called fetch page. It simplifies all those steps that I just mentioned. Transactions, I'm not going to go into detail. It's an extremely important subject, but I just want to look at the API briefly. The API is actually pretty familiar if you've already used the ex2.db library. See the book in the online docs for more information about transactions. Really important subject. But basically, we've got this notion of transactions where a transaction can only be performed on entities that are in these groups called entity groups. There's the strong, consistent transactions are not supported on the global data store because obviously it could be an arbitrarily large data storage across many, many machines. Entities in these groups that are going to be subject to transactions, and a single transaction can only execute on entities that are created in a single entity group. That's what I just said. There's a notion of cross-group transactions. I'm not going to cover it here. It's limited to 5 groups, and it's a little bit slower, but it's very convenient in some cases. But the basic idea here is that you write your functions, you write Python functions that operate on data within transactions, and then you use decorators to describe that, yes, these participate in transactions. If you're not currently in a transaction, you need to start one, that sort of thing. So it just looks like this. I'm incrementing the score of a player, and I need to be able to do this transactionally. I need to be able to read the score, increment it, and then save it back without having somebody interrupt me or overwrite the score attribute, the score property. So I create a function that does this. I say that it is NDB transactional, that's the decorator, and then I can just call the function, and it does exactly what I need it to. If you've got more than one of these that need to call each other, there are ways of using the decorator to say how they interact with each other. So in this case, I actually want the later call within increment score. I'm calling award trophies, and I want award trophies to participate in the same transaction that I'm in. So I make award trophies transactional as well, and since I've already started a transaction within increment score, it's actually going to use the same transaction to perform award trophies, and it'll keep track of everything. Okay, I'm going to go really fast I think I'm going to leave just a couple minutes at the end for questions because I want to just cover a couple of these things. I mentioned automatic caching, which is a really important feature of NDB. Really very common, I mentioned, to store things in memcache as well as the data store. There's also this other concept of caching where if you've got lots of code sort of separate and modular and you've worked really hard to keep it clean, you may have two parts of code in a single request that are operating on the same data. This is pretty common. And it's actually wasteful for one of those to go to the data store and get the entity, and then the later one also go back to the data store to also get the entity, because the first one already got it, and there's no reason to not use the same one. But to sort of couple those two pieces of code together so that they can just use the same value can be messy and difficult. So NDB has this thing called an in-context cache, where those functions can act like they're doing separate things, but NDB is keeping track. It knows that the first one already got that entity and nothing has changed or whatever, and so it's got a local copy of it in its in-context cache. The next time another piece of code tries to get that entity, it's just going to read it from memory. It's not going to do anything more. Memcache storage works the same way, and the same automatic feature, and these are features you can turn on and off for different reasons. So the context cache starts empty for each request, minimizes data store interactions. To turn it on, you do this thing. You set the context policy. So you get this context object out of NDB, and then you can set policies on it. The in-context cache, you turn it on with just set cache policy. This method just takes a function object, and it passes the when something happens, when there's an operation, the key gets passed to the policies function to determine whether to use the cache for this object or not. So in this case, I'm passing in a lambda that always returns true, which says all objects that I'm using everywhere, I want to use the in-context cache. So that's how that works. The memcache thing works the same way. Memcache, of course, is global and distributed, so it outlives requests. I use this in the content management system for developers.google.com, where if somebody requests a page of documentation, and if it's not in the memcache, it'll go to the data store, but then it'll put it in the memcache so that subsequent requests for the same page are actually going to read it from memcache, which is faster, instead of going to the data store. So many requests actually hit the memcache as opposed to the data store, and that speeds up the website overall. So that's really useful. It works the same way with the set memcache policy. The other important thing there, I wanted to read that one bullet point. NDB is actually handling the serialization of the model instance to go into the memcache. Previously with the DB library, you actually had to do this yourself, which is kind of fragile if you don't do it the right way, if the model representation changes and some other stuff. So NDB is doing some extra work there for you. You can actually set these policies on the class itself, and that actually overrides a global policy. So you can just say, yes, all player objects, please use the in-context cache, but don't use the memcache. That's what this would do. You can actually use the same thing to tell it, well, don't even bother with the data store. I'm just doing something tricky with the memcache here. You can disable the data store and just use the modeling class for something that just gets stored in the memcache. So that's another cool thing you can do. I'm just going to skip ahead here. The batch API is still there. You can do multiple things in a single call. But NDB actually has this awesome feature where it does some batching automatically. So it'll maintain a queue of things, and it won't actually call these things right away. It'll batch these things together and then perform them as single batch calls to reduce the number of RPC calls to the service. So it's a big speed win that it's maintaining for you. Maintains a consistent local view as it's doing this, and it only does it when it's safe, so it's not something you have to think too hard about. You can actually add requests to its own NDB managed queues for memcache and even URL fetch to take advantage of those same features, and you can flush them, things like that. There is an asynchronous API, so these services take time to perform what they're doing. If you need to do something else while the service is working on something you requested, you can initiate a call in a special way, and the call returns immediately with an object that refers to the thing that's happening on the service. It's called a future, a special kind of object called a future, so the application code can resume and work in parallel as things are going. Then when the app actually needs to use the results, it asks the future object, can I get the results, please? And it'll wait for the service to finish. So really powerful idea, lots of async methods. Pretty much every method that calls the data store has an async version of itself that does that. That's such a generally useful idea I don't have time for tasklets. I'm sorry. You're going to have to look it up later. It's a really awesome way to organize complex code. In the same way that NDB allows you to organize your code in various ways, tasklets allow you to write your code in such a way that it can make these asynchronous calls and yield itself to other tasklets so that NDB can manage all these asynchronous calls and just try to get everything done as quickly as possible. It's not concurrency exactly, but it's a way for tasks to tasklets to block themselves on service I/O so that other tasklets can execute, and NDB handles this automatically. So see the documentation. The online docs for tasklets are excellent. Go look at that. Okay, so I do want to leave a couple minutes. I'll stay a couple minutes late for questions. But I did want to point you to the official documentation for App Engine is on developers.google.com/appengine. If you want to sign up for an App Engine account and create your app, go to appengine.google.com. For more information on the book has a website, ae-book.appspot.com. So go check that out. I've got a little book blog and downloadable code samples and other extras and things that I might post there. The book, The Programming Google App Engine 2nd Edition, is coming out this month in a couple of weeks. Go check it out. Go place your pre-orders if you haven't already. And you can find out more about me on Google+. I'm at just profiles.google.com/dan.sanderson. Come follow me and look for announcements and other cool things that I might post. I'm now going to switch to the Google moderator to see what we've got. If anything. Questions. All right. Thank you guys for posting questions. I appreciate it. I'll just go down through a few of these. Would NDB on App Engine be a good candidate for a company's intranet site that utilizes most of the Google stack? Absolutely. One of the nice things about App Engine is a way to set up individual applications to work with your Google Apps domain. There are several really nice features for that. It makes it really easy to manage people's sign-in status with Google accounts. Lots of great features there specifically for that use case. So definitely look at it for intranets, especially if you're using Google Apps and other things. Basically, your custom app on App Engine becomes another app that is managed through the Google Apps interface, just like Sites or Docs or anything like that. So go check that out. Structured property versus key property, how are they different? They're definitely different. So key property is the value of a key property is an entity key. It is referring to another completely separate entity. If you're going to query off of, you can't perform queries. I mean, you can perform a query to say, does this property have a particular key value? But that's about all you can do. What structured property is doing is something very different. It's actually taking the model structure that you've set up, and it is creating properties on the original entity based on those model fields. It's very different, and I think the main difference between them is whether you want those properties to be queryable. You want to ask, give me all the players, go back to my example in the slides, give me all the players whose home is in a particular sector. That is the kind of query you can do with a structured property. Now, you may or may not want, basically it's embedding all that data within the single entity. If you need to query the separate kind of entity separately, so if I want my player homes to be their own separate entities so that I can do something separately with those entities, then I would use a key property and then forego certain query things, or I might denormalize some values from the home into the players if I want to perform certain kind of queries, other techniques like that. But that's the main difference, and that's a very good question. So NDB is basically using its modeling idea in multiple ways in that case. What full-stack Python web frameworks work with NDB? Lots of the major ones. Django works. In fact, developers.google.com is a Django application. Some even special support for Django in there. Web2Py, Pyramid, Flask, some of the smaller ones like Flask. App Engine ships with a small one called WebApp2. Definitely look at that one. All the major ones do because they're all WSGI. Anything that has a heavy reliance on relational databases might not work, but that's one of the cool things about Django is that there are lots of useful features of Django that even though traditionally Django uses a relational database heavily, there are ways of using all of its components with App Engine to forego that part, and even ways of using its own modeling interface with App Engine. What solution or library would you recommend for building a RESTful API on top of NDB? There's got to be a really good framework out there for just like mapping NDB objects to a REST API. I don't know any, but they're usually pretty straightforward to set up. In fact, it's easy to imagine something that translates NDB models directly into REST calls, but I don't know one. Definitely we should look it up and find one and post about it. What third-party hosted continuous integration and continuous deployment services work with Python GAE? I'm not familiar with many. I certainly there's one that was mentioned in the on the App Engine blog itself recently. Go check out the official Google App Engine blog and scroll down a bit. There was one that was mentioned that is really compelling. I know of some people that have set up their own, but have not made them publicly available. So there are ones out there. The main one I know about is the one that's mentioned in that Google blog post, and the name escapes me at the moment. So go look that up. Let's see. Key idea: NDB is used to reduce code overhead in cloud APIs. Speed. Database. Yeah, generally the right idea, AJ. I would agree with some of this. Let's see. So yeah, NDB caching is definitely a very common pattern, and NDB is managing that for you without you having to write extra code. Of course, more code is more complexity and more to manage, more error prone. So having NDB work on this stuff at a framework level is really useful. Yeah, data structuring. I don't know if it's not necessarily going to reproduce all the features of a SQL database. So I don't think I would go all the way in that direction with a description of it. But yeah, you've got the right idea. How would you normally traverse relationships across entities? MapReduce with denormalization, the answer here. In some cases it is. It really depends. I mean, this question is very domain specific. I've certainly done both of these in the past. And there's right now the MapReduce as a general concept is applicable to App Engine. I'm still hand-rolling my own tasks at this point with the Task2 service, but I have used the experimental MapReduce library in the past with good success. It's another great framework that's still experimental. It's worth playing with and looking at, but in many cases I've done smaller task jobs that way. In other cases, yeah, it's worth the extra time to traverse the normalized data, depending on what you're doing. Sometimes you have to build things into the user interface for it to wait for longer queries and that sort of thing. But yeah, those are both options. Kind of depends on what you're doing. And that's it for what's on the moderator board. I don't see anything else. Yasmina, if there's anything on Twitter or anything like that, feel free to mention it now.
Nope.
Okay. In that case, thank you guys very much for coming. I really appreciate it.
Great. Dan, thank you so much for presenting an extremely fantastic live event for us all today. Folks that attended, we thank you for attending our event and hope you've enjoyed it. We'd like to let you all know that O'Reilly Media does have several free online events. Please visit O'Reilly.com. Right here is our free online events. We have so many great topics and presentations. A lot of them are going to be done via Google Hangouts on Air. Important thing is these are all free, and O'Reilly likes to spread the message and knowledge of innovators. So please, folks, if you want to learn something new, spend an hour with us. Check out our free online events. Again, thank you, Dan. Thank you, everyone. This will conclude today's broadcast. Have a great day, everyone. Goodbye.
Bye, everyone.